So thank you very much. I'm very happy to be here in Italy. Okay, so I'm going to target strongly correlated systems, particularly in chemistry, but also in condensed matter theory and nuclear structure theory in the end, by thinking about it the way we think about weakly correlated systems in chemistry. So weak correlation is ubiquitous in chemistry. Most systems are well approximated as weakly correlated. So anything that's dispersion, where there's one Slater determinant that dominates the wave function, you can guess that it's weakly correlated. There are many problems in chemistry, however, that are not weakly correlated. Whenever you want to stretch or break a bond, whenever the motion of the electrons is coupled very rigidly, when there's more than one Slater determinant that's important, when there's more than one resonance structure you need to qualitatively understand, or whenever the HOMO-LUMO gap is very small with respect to the inter-electron repulsion energy of the valence electrons in particular. If you find yourself needing to ask the question, how many bonds are in this molecule? Probably it's because it's a strongly correlated problem and the concept of bonds is ambiguously defined. So any system that is not adequately described qualitatively as a mean field of electrons forming around some strong potential, I would say is strongly correlated. Is that a productive way to think about it? That's more of a conceptual question. Can we try and subdivide that into effects that are easy to understand and treat them individually at the mean field level with a wave function that describes what's happening? So in the weakly correlated problem, this is very easy. You choose a system that well represents qualitatively your system, Hartree-Fock, and then you expand an ansatz for the wave function on that basis. And that should converge reasonably quickly, provided your starting point is good. Otherwise, there's no reason to start from this, and I would not. Can you define a reference for strongly correlated systems such that you can do the same thing? And of course, that's going to depend heavily on what your system actually is. But you can try to choose sub cases for interesting case for individual cases. So the first step is to look at seniority zero. And it's been shown that that is a productive way to think for many strongly correlated systems in chemistry. And you can adequately describe that as weakly correlated weakly correlated individual pairs of electrons rather than weakly correlated electrons. So when we talk about seniority, we can draw many different molecular orbital diagrams. And each of these diagrams on the left, all the electrons are paired. So there are no unpaired electrons. Otherwise stated, there is zero seniority. In the diagrams in the middle, each of them has two unpaired electrons, or they have seniority 2, and seniority 4, etc. And you can continue until all your electrons are unpaired, and you can classify your Slater determinant basis in that way. So the best possible case for mean field of pairs is all the diagrams that are seniority 0, which we call doubly occupied configuration interaction. And I will be very clear that I call this DOCI, not DOCI, just so there's so much confusion later. And a mean field of pairs has DOCI as a best possible case, because if you would expand it in a Slater determinant basis, they would all have seniority 0. So if you look at the dissociation of nitrogen, and you cannot see the reference, but it is a paper of Batatas and Scrisaria from 2011, I believe. They look at the dissociation of nitrogen. You can see RHF is not even qualitatively correct at dissociation, but already when you only include seniority 0, which is this blue curve, you get something, I mean, it doesn't look size consistent here because it's only 2.8 angstroms. At the dissociation limit, it is flat. So it is at least qualitatively correct, if not quantitatively anything reasonable. As you add more seniorities, you approach the full CI answer reasonably quickly. But the important thing to mention is that even the seniority 0 problem here is already full CI cost. Okay, full CI cost, square root of full CI cost, which, great. So even the seniority 0 problem is not something that you would tractably do on a computer every day, except today, because I'm going to show you how. Okay, so the language we work in is pairs. For individual electrons, you have usual Pauli relations. You can make a pair of electrons in each spatial orbital. You can remove a pair of electrons and you can count the number of pairs. And these things satisfy the same algebra as spin. It's isomorphic. And you can do that in any number of levels with the only added complication that you have Kronecker deltas between them. So isomorphic to spins, we should think in terms of spins. And then we can build mean field wave functions out of this. The thing that I really need to highlight is that we already think in this way because RHF is one of these things. It's not a good one, but it is one of them. So in principle, anything you can do for RHF can carry forward for others. There are many others. So AGP in particular, where all the pairs are the same. The ones that I use are Richardson-Gaudin states that we will get to later. The idea is that your coefficients are parameterized by two sets of numbers, one that is physical that you vary and the other that you have to solve equations for. If you let both of them vary, then this is totally unfeasible and we can forget it. The most general wave function of this type is just fully general pairs, and you cannot do that variationally, completely unfeasible. But there are others that also exist, so GVB, and you can play a drinking game because I would say GVB a lot. So APSG is very similar to GVB, except that in each pair you have a block of orbitals, and those blocks are what we call strongly orthogonal. So they have to appear only in that block. Finally, there's paired couple cluster doubles, which is very good for many chemical systems, and we'll talk about it later. It's the bane of my existence. You cannot do it variationally, but projected, it's very good, and it's n to the fourth cost. So why am I going on a length about this? Because geminal wave functions are more or less the same as natural orbital functionals. They can either be explicit, like APSG, GVB is piano of 5. AGP, the two matrix, is a direct function of the natural orbital occupations, or they are implicit. So for RG states, to compute the two matrix, you need the same variables as the one matrix. It's not explicitly defined, but implicitly through the equations, they're the same variables. It's the same thing for APIC, except it's just totally unfeasible. And I apologize for the names. We are stuck with them because the literature exists. Okay, so we go to RG states, which are the eigenvectors of a BCS Hamiltonian. You have two competing effects. You can fill the lowest levels, or you can scatter isotropically between each of the states. So this wave function in the thermodynamic group of pairs, but you can solve it at any particle number with the straightforward approach. So Richardson, or later Gaudin, showed that if you take this ansatz for the eigenvector, and then you act on this vector with this Hamiltonian, you will get one term that's proportional, and then a bunch of nonlinear garbage that you want to get rid of. So you clean up the garbage by solving the set of nonlinear equations, which we call Richardson's equations. So I will just say that you do not solve these equations directly because you have these diverging terms between the two sets of variables, and that is bad. It is very difficult to solve these equations. The first two terms look very similar to Cooper's solution, and then the last term is like a repulsion between the pair energies. So there is some sort of Pauli principle here. Okay, so that is all I will say about them for now. We're going to take the ground state of this Hamiltonian, and we're going to use it as an ansatz for a chemical system. So that means our variables are going to be the set of single particle energies and the pairing interaction. At each step, we have to solve Richardson's equations for the U. I will not be precise about how for now. And we construct the normalized density matrix elements. So this is very strange for me because if you read my papers, you will see that 98% of what I do is very tedious expressions to get at clean expressions for these matrix elements. So here I'm only presenting the results, and we're not even going to present the matrix elements. If you would like to discuss them, I'm here all week and I will bore you to death. That being said, you can construct this matrix at n to the fourth cost. No problem. And you can solve Richardson's equations for cheaper than that, which is important. So the system, that your physical model system, is defined by the single particle energies in your parent strength. You solve for the U's, which are more or less pair energies. So you do this for H2 and you get a result that's, exact. You cannot see, but there's a point that is missing up here. And you can't see the energy scale, it's 10 to the minus 11. So I would say these two things are numerically identical. So great, H2, congratulations. You've done a diagonalization that you give to an undergraduate as a homework problem. You go to H6 and it's not even close to being correct. So there's a problem here, which we will get to. So this is the point where you lose all faith in your method and you have to go to the brute force approach, which is you just do the APIC solution, which is completely unfeasible. And I will not go on about these matrix. We'll just skip the density matrix elements, but there is a very clean answer for there is a very physically relevant answer for the matrix elements of APIG that is completely unfeasible. And they're reduced to feasible expressions in 3 distinct ways, and we can talk about them later. So we do the same calculation for, in this case, H6, using the ground state of that Hamiltonian I showed you. With AGP, you can see it's not even close to being correct. It's not size consistent at all. The same form as the ground state of RG, except you do not force the pair energies to be solutions of these equations, and then with A big and Doki, which are unfeasible. So the point is that if you do not force the pair energies to satisfy these nonlinear equations, you get the exact answer. And you can see the difference between them is very small. Now, this is completely unfeasible in general. The point was maybe a different state of that Hamiltonian is fine. So if you do that, you see that the error is very small. The other thing, we didn't talk about that, so we'll just, there's something that we blew past, so we'll just continue. Okay, so if we use the wave function form, but do not force the nonlinear equations, we get the correct result. Great, but that's totally unfeasible. Maybe we can use a different state, different eigenvector of the same Hamiltonian to get the same result. And that was what we supposed, and then we ended up showing it before the paper was published, so it was much easier. So now we have to talk about how these states are understood and defined. Each eigenvector of this Hamiltonian is defined by a solution of these equations. For each state, you have to solve a completely different, you have to solve the equations completely. And the solutions are not related, well, not related. Each state is defined by a distinct set of U's. They don't share any elements in common, is what I'm trying to say. They would be close in numerical value, but they are not the same. So the way you do this is you do not use these lowercase u's. You define these different variables that are where the u's are traced over. You get a different set of equations, which are much easier to solve numerically, very stable with cheap numerical expressions. So you no longer have diverging denominators between your system and your pair variables. So this is way easier to solve. And you do it by evolving from G equals 0. So when G is 0, everything is non-interacting. Slater determinants are the eigenvectors. You can clearly label what the variables are. The part that is not so obvious, but once you do it numerically, you will see that the states evolve continuously from those from Slater determinants. So at any non-zero G, you can uniquely label your state based on the Slater determinant it evolves from. So I'll show you an example. Okay. Until very recently, you needed to compute these U's through this complicated numerical expression once you have the uppercase U's. Now, all you need is the uppercase U's and everything is much more stable. So that is on archive. And if you happen to be a reviewer for that paper, we are patiently awaiting your referee reports. Okay, so how do these energies look? This is a 4-site 2-pair pairing Hamiltonian, and the states are uniquely defined by their occupation at G equals 0. Okay. 2 of them are degenerate, so you only see one of the curves, but otherwise you can very clearly see that they evolve uniquely from the G is equal to 0 limit. So it's fine to label them based on that occupation. The important point about this is that to solve the equations on the previous slide, it only requires a logarithmic number of steps. So as you increase the pairing strength, the difficulty only scales logarithmically with the size of the pairing strength. And this is not a small system. This is 40 sites with 20 pairs, I believe. We can do 100 sites with 50 pairs, no problem on my laptop. 1,000 sites with 500 pairs, it takes a little time, but there's no problem. And it scales pretty favorably. So we go back to our hydrogen chains, which were not good. And we're going to compute using all the possible states. So what we had before was that the ground state, which is 1100 always, is not correct. There's this unphysical local maximum in the middle. Then 1001 is not physical either, but 1010 is very, very close to the exact result. And if you look at the difference with Doki, it's, anywhere past 3 Bohr, it's undetectable. And in the weakly correlated region, it goes up to like a millihertz. Okay. Minimal basis. So This would be worse in a real basis. But in a weakly correlated region, it's not so bad. In a strongly correlated region, we're essentially exact. What is happening? So if you plot the model parameters, which are these single particle energies, you'll see that you have two very near degenerate sets, and the pair energies are essentially trapped between them. So what happens is that at dissociation, you essentially have generalized valence bond pairs, which is KNO5. And at the minimum, it is essentially Hartree-Fock plus pair doubles. And the transition is smooth. So there's no discontinuity. Well, in the energy, there's no discontinuity. In the wave function parameters, there's this kind of not great point in the middle. But if you look at the density matrix elements, everything is smooth, even the two matrix. Okay, again, H4, not a particularly large system. So again, you cannot see the top. Once we have optimized the single particle energies and a pair interaction, let's just compute all the states to see what they give. And they give the DOCI results, all of them, just by computing the other states that we had with the ground state. The only thing that we do not get is that in the fourth and the highest state, there's an avoided crossing in the middle. From our mean field solution, we're not going to see that. We would have to do a 2x2 CI diagonalization, but that confirms to me that we are looking in the right picture. This system is well described as non-interacting pairs, and you only need one RG state to describe any of them. So the day after this was put on the archive, I got a very polite email that reminded me that these are not the physical excited states. Why? Because each of the states requires a separate orbital optimization, and that's very hard. However, the Doki and RG states are indistinguishable aside from avoided crossing. Okay, and this continues. So H8, it's the same story. Essentially exact the dissociation and deviating linearly in the weakly correlated region. Which RG state do you have to choose? 1, 0, 1, 0, 1, 0, 1, 0. I mean, in principle, if you had to choose that out of your hat, that's an NP complete problem, but I think that one's pretty easy to see. For nitrogen, it was less obvious which state to choose, but in the end, it's very, very understood physically. You have 4 orbitals that are totally occupied in your core, and then you have 3 GBB pairs. So the state 1, 1, 1, 1, 1, 0, 1, 0, 1, 0 is the one you want. And the difference between Doki is almost 0. Again, except in the weakly correlated region. I have more results for diatomics that I will not show you that would confirm that it is easy to choose the state that you want. So NP complete problem, at least avoided in this case. Okay, this is all one vector with end of the fourth cost. We have a Hamiltonian. In principle, we have all of its states, and they form a basis for the seniority 0 problems. So we can use more than one. Each state is parameterized by a distinct solution of the equations, which are easy to obtain. The transition matrix elements are a little tricky at the moment, mainly because we haven't finished working them to make them clean. You can guess at the energetic ordering of the RG states, but on paper, each state couples with each other state in a non-zero manner. It's not like Slater determinants where you on paper have a 0 matrix element between states. But if you look at it numerically, they die down pretty quickly with excitation. So the 2 transition density matrix elements that you would need are NN and S plus S minus, and they go to 0 pretty quickly. So this is 10 sites with 5 pairs. It's not that big. You can see that the singles are incredibly important. The doubles are important, but less important, but non-zero. And then after that, it goes to 0 essentially very quickly. So you can do a finite size CI in this basis. And for a seniority 0 problem, you should get the correct answer pretty quickly. So the point is we're building methods for strongly correlated pairs with RG states. It is variationally feasible. You have a physical mean field that you understand with a complete set of eigenvectors and clean, easy expressions to compute. If I can program them in Python, anyone can program. potential for sparsity that we'll not discuss. The main problem is the orbital optimization. And this is a problem for everybody, so I don't feel so bad about it, but it is a problem. The orbital optimization is difficult. There are local minima that we need to avoid. So how do we know that we have the right orbitals? In the examples that I showed you, I had someone compute them for DOCI, then I used them to make sure I could get the right answer. So that's cheating. The optimization we haven't worked on. How do you choose the correct RG state? I have results, but I'm not going to present them to you. And the other two things we are working on now. So for the problems we looked at in chemistry, it's very clear that you only need one RG state to get qualitatively what's going on. Okay. This is not difficult to use. It's the point. You should use it. It's not difficult. I will teach you everything you need to know. So we looked at some more difficult systems, and here I'm not presenting results. These are just the exact curves. This is not quite harmonium, I understand, but the potential does depend on harmonic oscillator matrix elements. I'm not confident enough to say it's harmonium, but they depend on harmonic oscillator matrix elements and some parameter. As you increase the parameter, it is very strongly correlated. I've seen curves that would suggest that PNO at 5, I think, is qualitatively correct, but you can still distinguish the results. I will tell you that in this strongly correlated region, one RG state is incredibly important, and then its singles gives you numerical accuracy to 4 or 5 decimal places. So that problem is completely solved with one RG state plus its singles, but I'm not going to present the numerical results because they're not done yet. Another case where you need more than one RG state is a nuclear structure. So the isotopes of tin are very well described as pairs of interacting neutrons. So you can totally forget the odd numbers in this series, but the even numbers all have a seniority 0 symmetric ground state, and they're incredibly well described as interacting pairs of neutrons. The protons are a completely closed shell that do not matter. One RG state is dominant, but you need a short expansion to get the exact result. And this has been done by my colleague, and the results I would say are pretty convincing. A much more difficult problem that seems counterintuitive is isotopes of calcium. So calcium would in principle be a closed shell of 20 protons and a closed shell of 20 neutrons. So that should be an easy problem, right? But it is not. There are way too many states in the spectrum, and it's very complicated. So the point I wanted to make is for isotopes of tin, it's an easy pair problem. I would believe that you could you could write down a 1 density matrix functional and get this correct. Not the excited states maybe, but the ground states. I would be incredibly surprised if you can write a density matrix functional that would get all of these states correct. So here you need to use RG states, and I haven't done it, but all these states are seniority 0, and they're sort of near the ground state in energy. So it's complicated. Okay, so thank you very much for being very patient with me. I have a group who has worked very hard on these results, and the names in bold are currently my students, except the last one that but anyway. So if you know any people who are looking for a PhD, like doing equations on paper and can do some very basic Python, please let me know. Always interested.